This is the screencast for section 7.1, example 7. We have a bit of work to do. Hooke's law for a spring says that the force it takes to stretch or compress a spring x units from its natural unstressed length is a constant times x. So in symbols that means F equals k times x, and we'll call the force constant k. Now work is force times distance. So kind of like the work we're doing right now is the force times the distance we're at. Well, example 7 asks us, it says it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done in stretching the spring 4 meters from its natural length? It's asking us for a total amount of work, not just the work at 4 meters, but a total amount of work. So first I got to find my force equation. Force equals k times x. So they gave me this initial situation where it took 10 newtons to stretch the spring 2 meters beyond its natural length. So I solve for k and I get k equals 5. So my force equation is 5x. Well, now I can plug that in to work. So work equals force times distance. So my work equals 5x times dx, or basically dw. And then the total work then will be the antiderivative from 0 to 4. So the total work between 0 and 4 seconds of the force times distance. And with a little bit of integration and fundamental theorem part 2, I get that it's going to be about 40 Newton meters. Force is measured in newtons, and then distance is measured in meters, so that would be Newton meters. The now try problem number 29 also talks about Hooke's law. It says a certain spring requires a force of 6 newtons to stretch it 3 centimeters beyond its natural length. Part A asks what force would be required to stretch the string 9 centimeters beyond its natural length. So first I got to solve for that k value by using the situation they gave us. So force equals k times x. I'll plug in 6 newtons of force and 3 centimeters. Solve for k, and I get my force equation is 2 times x. Well, now it's asking what force would be required to stretch it 9 centimeters. So I'm going to plug in 9 for x, and I get that the force would be 18 newtons. Now part B, what would be the work done in stretching the string 9 centimeters beyond its natural length? So not how much work at 9 centimeters, but what work would be done in the whole stretching from 0 to 9 centimeters. So I need to set up my work equation. Work equals force times distance. So my total work is going to be the antiderivative from 0 to 9 of my force times distance. Then integrate fundamental theorem part 2, and I get 81 Newton centimeters this time, not Newton meters, because we're only stretching by 9 centimeters.